Okay. Um, we discuss the exercise list. Yeah, we put in, um, Senator species of chapter 7. Chapter 7 we can move a piston from 25 in this case. We will receive the 5 bar. The piston is slowly moved with plastic press. So, considering the case, the system to be case on the cylinder, getting the water into should energy, we can simplify the flow system managing data. Do not assume that process is exactly spot. So this is a step by step. So normally we start with the phone equation, the tree system, the clock system. You see it as the internal energy unit, right? So simplify, so non-kinetic energy because it's stationary, and I know potential energy expression left with delta equal to H minus Q minus W expression. Suppose now that the process is carried out isothermally and the compression work done to case equals 7.65 with the bar. If the case is ideal so that the internal energy, specific internal energy, is a function only of temperature T, how much heat in joules is transferred to the surrounding. If the gas systems conversion. For this one, so constant T because they'll tell you the angle changes to the specific internal energy. So the expression left is Q equal to W, but W is in liter per unit. Heat is in joule to do the unit conversion. So final answer negative 765 joule. Just went from the gas to the surrounding. Just to look done by the system that on the system. The next is suppose instead that the process is automatic and that specific energy increases as temperature increases. Is the final system temperature greater than 0.2 or less than 30 degrees? So for adiabatic, now Q is equal to 0 and delta U, because delta U is increased, because T increase. For the second question B, T is constant, suitable, so delta U is 0. So for this case, delta U equal to the value equal to 7 the bar which is 0. And since the temperature increased with the internal energy, so the final temperature is okay, 30. Second question. A is heated from 25 to 114 degrees C prior to entering the combustion furnace. The change in specific enthalpy associated with this transition is 33.9 joule per mole. The flow rate of A is 6 And make sure at this point it's 122 kilopascal absolute. After the heat requirement in kilowatt, so we measure gas behavior and the key measure energy changes from the heater inlet to the outlet negligible. So A is heated in factory property and entering the next. So first thing you need to do is draw the changes we for A the heater outlet is my basis. And the energy at this point is 0.3 Pascal. Get that? So since given specific enthalpy here in mole, you need to remember specific enthalpy is sometimes it's in kilogram, it's joule per kilogram, and in this case it's per mole, so joule per mole. So since it's in mole, you need to convert the molar flow rate, the volume flow rate to molar flow. So how to do this? You need to STP. So STP is 22.4 liter per 1 mole. But with STP, there are temperature and pressure. That's why you see 101 and 273 maybe. So in this case, 110 per minute. This temperature. So the temperature for 23 is actually 55. Okay, so in this case, it's a 1.65. Depending on the one. So the flow rate here should be in the outlet. Okay, let's see. Take the rule. The outlet. So this one is 1.65. Six four so 1 2 subject 53. So 1.65 is based on patient 65. This is the outlet temperature. Refer to the patient. It's right of A at the heater outlet. The stated condition We get 43, not 43, 30, 48. Keep it more clear. So this is expression for chemical, expression for the open, consistent. This is just a conversion furnace. There are no shaft moving. So Q equal to delta H, which equal to N times specific enthalpy. So the specific enthalpy is in joule per mole. 36 3349. This is 3349. So molar flow rate in dot the mole per minute the position time 3349 joule per mole is from the pressure conversion conversion you get 2.79. More information would be needed. The change in kinetic energy would depend on the cross-sectional area of the inlet and outer pipes. Hence, the internal diameter of the inlet and outer pipe would be needed to answer this question. Oh, the one is another question. Next question. What the value of kinetic energy? Just the this part. Be positive. And what you need more information to be positive into what information you need to. So to do this question, change in kinetic energy will depend on the procedure, which is to place the internal diameter of the part on the part that the unit is registration. So for this uniform, you can refer to which was okay. 359 relation for the. 0.6 The velocity involved flow rate divided by cross-sectional area. So n n dot in this case n dot over a. Okay, K x is saturated still. Saturated steam a gas measure of 2 bar is to be used to illustrate ethane. The ethane in this is 16 degrees C, 1.5 bar gauge. It is heated at constant pressure at 72 degrees C. The steam condenses and with the exchangers keep at 37 degrees C. The specific enthalpy of ethane at the given pressure is 141 kilojoules per kilogram at 16 degrees C and 0 pressure at 2 degrees. So in this question, specific enthalpy H delta P is given because we cannot find the answer. So find the information in the back of the book. It use is how much energy must be transmitted into the from 16 degrees C to 33 degrees C. Okay. So first thing, this is we can have two component. First thing you need to do is to draw the so we have two inlet, but the inlet is not it's not mixed because this is a heat exchanger. This one you see that separation hole, separator, steam enter on top of the thing. Enter entry bar, show how much, but the phase change from liquid to liquid. Ethane 16 to 93 degrees C, pressure maintain 15.5. Okay. So first thing we need to do, check the specific enthalpy. If it's in mole, so you need to do this, change the flow rate to molar flow rate. Since the specific enthalpy is over mass kg, so you change the flow rate to kg. So to do that, for molar flow rate, there still there are there are there's no other way except for using STP value. But STPF is all but from less low kg per minute. Is this just enough? Not really. Not really PP and happy. This is just a normal unit conversion. Oh, to convert to mole flow rate, just use SDP. Yeah, because check the standard temperature and pressure. 2.4. So STP. It's STP. Oh, it's I think it's miss correct. Correct. Using PV and RT. The need to state the PV and RT is, yeah, it's easier like this. So for polar flow rate, just use STP. Just plus it will should do not find the emission at the table. You can assume PV and RT. STP actually derived by from the ideal case equations. But if you can use PV and RT to find the polar flow rate, yeah, can be done as well. Still need to check. If you get 58 one per minute, if you follow this method, okay, it's straightforward. So for keeping for molar flow rate, you will refer to this method. So this is the divert 1.65. 273 is from the STP. 413 is outlet for the system. 101 is the STP. 122 kPa is the system. Why it's arranged like this is because of the unit for the STP. So unit should be 122.4 liter to kPa over mole the dot Kelvin over mole kPa. It's okay. 7.28. So conversion for the yes flow here. Okay, so for this conversion, this is 3.5 terabar. With 9 Kelvin. Okay. Check the conversion, mass flow, molar mass for the 10 step 46 to the kilograms. And the unit conversion. And we get 2.487 Kelvin that of 3 kg per minute. So HEI in 10 into P10 final, 10 initial, 10 final is given. So for the omega balance, start with the just write the full equation is then rectify which term is 0. In this case, this is just a big thing. Okay, so there are no chemically look. The AP is 0, with the K is assumed 0. Q is equal to the H X value. Specific enthalpy unit, the final unit is in kilowatt. I think most even can take 3 kilowatt. This is the first station. How much energy required to must be transferred to attempt to hit it from 16 to 93. It's required 5.47. So now, next question is, assuming that all the energy transfer assuming that all energy transfer from the steam cost to hit the ethane at what rate in meter cube per second must steam be supplied to this exchanger if the assumption is correct? Would the calculated value be too high or too low? So in this case, the unknown heat losses to the surrounding. So H is 1 3 bar saturated vapor. It's 1. This refer to the inlet here. So enthalpy for the specific enthalpy for the inlet is 2724.26. This is HS2. It's what? It's 113.1. Table V5. Assume that it losses to the surroundings given, so that the heat given by the condensing steam equals the heat transfer to the thing displayed. So the energy burden on the water now Q equal to delta H. The term remain. Actually, it started with the full equation, then simplify to Q equal to H. Okay, and of flow rate specific enthalpy. So they use M here because specific enthalpy is over mass kg. If it's over mole, it's using M. Okay, so for M, okay, get 2.09 kg per second steam. Calculate further. S volumetric flow rate 0.606 0.526. Take it down. So in table 6 F volumetric flow rate. You have it in two condition, the water or steam. It's page 646. When you get 1.27 meter cube per second. So from this question, the steam flow rate is too low, extra flow would make up increases to surrounding. This is, see, if the heat is not lost to the surrounding, so the flow rate required is just this much. But to the ethane, it's actually required to up in the number. So for ethane, it's actually 40,700. Yeah, per second. If you convert into 40 per second, compared to 1.27, the cube per second. Very far. Next, chemical energy. Ethanol is contained in the large tank. Not sure which one you took, but for this question, running. If we do the yes, I did check because this is okay. It will be fashion, this is good. Oh yeah, thank you. So for in page 642, at 27 degrees C, they are not 27, they have 26 centimeters. So you need to do a calculation to get the specific enthalpy. So for this case, specific enthalpy is in matter form. The non-contain, okay, second one bar when above is bar. Bottom of the plane is open. The ethanol runs freely through one's end ID. The method push outlet is 7 meter below the surface to the ethanol to measure the outlet of the discharge price. Use the Bernoulli equation to estimate the ethanol discharge velocity and flow rate. Determinate with the discharge of speed open. We take the rate of fall thing. So the Bernoulli itu equation siapa? 376 7. Refer to question 7.7-3 compared to the mechanical and general equation. You can see there are no term for friction and shaft work. So meaning there are no friction involved in this system. And yeah, based on the diagram here, there are no mechanical work as well. So point one surface of the fluid here. It's 3.1 bar. Piston 7 liter. And U kinetic is 0 meter per second. H. Let's check this. Point two discharge pipe outlet here. P2 is 1 liter or 1 bar. Z is 0. U is unknown. Actually, there are U for the surface of the fluid. When we open the valve here, but the value is very small, neglect it. That's why it's U delta rho over rho. Okay. The rho ke delta P itu ya. So delta P ya. So delta P over rho so to the relation to 1.013 minus 3.1 bar 0.2 minus 0.1. So to answer this question, you need to be firm. Which one is 0.1, which one is 0.2? Because later on delta P is 0.1, sorry, 0.2 minus 0.1. In this case, it's different. Then this is a information. This is the city. P. So the density. So this is density for the ethanol. It means 792 kg per meter cube. So the expression delta P over rho is equal to negative 263.5 meters per second squared. This is the second term. G delta Z. Okay, this is the gravity. Minus 7. So that's why I said to make sure which one is 0.1, which one is 0. And stick with it. So delta Z is equal to Z2 minus Z1. So that's why it's negative. So you get negative 68. Can you see the unit is the same now? If the unit is not the same, then you cannot simply add the Bernoulli equation. So you need to write the full Bernoulli equation from delta P borrow until 0. Then you arrange it. Split the unit to left hand side. Okay, since its unit is the same, so they just write 8. 2.1 delta U squared over 2. So delta U squared equal to U2 squared minus 0. You see the button of confirming which one is 0.1 and 0.2. It's easy for you to make mistake. So for you to sway, let me get 208 per second. This is the velocity. So for the next question is the flow rate in meter per minute. Let's just mark screen open. So this one should will involve the cross section of the pipe. The tube is a tube. So pi k 16 5 cf per second. So 250 cf per second is from the unit. The velocity unit is cm. And assume something with the heat. So you get 122 meter per minute. When the discharge when the discharge valve is partially closed, the flow rate decreases, which means that the used spray bubble fill changes. However, the other two terms, trigonometry that continue to present the same. We the concept is the following contradictory result. Okay, so we're partially close. The friction loss term of question 7.7 just two. So 7 inverse, yeah, 7.7 just two, which is referred to the mechanical energy balance, which was dropped to derive the Bernoulli equation, become increasingly significant as the valve is closed. Oh, okay. Secure questions. Yeah, this is question. 5 minutes. That
Not yet, sir.
fabulous. Mm. What about it?
Millisecond.
Sure. Still, for the 16-second batch of the standard Amazon K200 So system-wise, one inlet, one outlet. Variable heat is transferred from the nozzle to its surroundings, so Q is 0. This is just the line. Okay, just a nozzle. So there are no mechanical work. So W is 0. The cross velocity of the steam is different. Okay. So there are no initial velocity. The specific capacity of steam is 3974. Okay. if the enthalpy of steam is given, so we need to check that. Paper B6 or B5. Use the open system given the exit steam velocity of. So to answer this question, write the question first. Delta H plus delta K plus delta P equal to Q minus delta S. If the QWS is 0, then left with delta EK and tau P expression. So delta EK is into negative delta H equal to equation for the kinetic is mu square over 2. So mu square over 2 is equal to enthalpy. So enthalpy is equal to mass times specific enthalpy. So what's 7.2-1 equation? And equation 7.4-14a. So for the delta EK, it's actually both 7.4-14b, but since the initial input for kinetic 0, so I'm left with mu square over 2. So, I'm not sure. Check. Oh, okay. So, ito na. So since velocity for the inlet is 0, so this is the velocity for the final or the outlet stream. And you get back to okay. This is expression for the algae. So you spray equal to minus station out. M let's go let's cancel out. Sama. So if program you consider performance, this is given equation, unit conversion from kilojoule to per liter, then another conversion then to kg with the speed get 477 with the basic. So 2.2 and then okay, this is this second square. Don't forget you square the square root this and you get the second square. It's more than first chapter. Right. So Do we have class for this?
Yes, sir.
Oh, yes, okay. Then we finish and is it online or face to face?
Face to face, sir.
Face to face. Finish at 9:15. Just 11 minutes. So this is second chapter for the book chapter 8. This is the main energy level. There are three non-reactive, reactive, and transient energy level. So you will need this at least two lah, non-reactive and reactive. Your IDP. This. So this chapter present procedure for writing data hash for the value when table of specific enthalpy or specific internal energy are not available for all process species. Once this location has been performed, evidently may be written as rough as before. Line procedure for solving given problems that will be applied to both non-reactive process and reactive process. So what is a non-reactive process? There are no okay, yeah. So reference state. We call that the first thing. We can never know the absolute value of U for a species at a given state. So the energy is the sum. This value, therefore, bedroom number which since that dash to plus B, we cannot learn the value of U. We also cannot learn the value of the shape that specifies state. Fortunately, we never need to know the actual value of the shape specified state. We just need to know the specify changes of state. Calculating this particular spending, we may probably choose a reference state for a species that we needed. It's based on the reference state. Actual specific number for the U at that certain position, we don't know. The value of the equation is developed using this procedure, which is true. Reference state was used to be liquid at triple point. So this is the state. You see the table B5 and 6 is based on this reference state, at which point U was defined to be 0. So the table B7, 5, 6, 7. 7 is always supercritical. Water vapor is 400 ppc, 10 bar. U is 3958. So this does not mean there is a value of U. Its specified state is 2958. Remember, we cannot know the actual value of U. It means that U of water vapor at 410 bar is 2958. Still. So 2958 is based on reference state at triple point. So that is the fundamental why we need the flow state. Relative to water at the same reference state, the specific enthalpy of water vapor at 400 degrees C in 10 bar is H equal to U plus PV. So, to identify H, you can use this equation. 2958 is from the table, table disabled. And plus 10 bar 53 or 7 to persistent density need conversion and conversion. So 10 bar 0.307 that will be saved. Correct. 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 Page 651. 958. So it then so specific enthalpy in this condition is 3264 kilojoule per kilogram. So this value is actually referred to the R state. Exercise. Suppose water vapor at 300 degrees C is minute. 5 bar extrusion as the state which is defined to be 0. Relative to this state, what is the specific enthalpy of liquid water at 75 and 1 bar? What is the specific enthalpy energy of liquid water at 1 bar and 1 degrees and 1 bar? Right. So at 300 degrees C and 5 bar is chosen as the reference state. It is 0 relative state, but is the specific enthalpy of liquid at 75. Okay, cari deh. Berapa? Cek. Satu bar 75. Oh, udah ya. Cek. Oh ya. Sedikit enthalpy. Enthalpy H 314. It is 314 for the 75 and 1 bar. Next is you need to find, suppose what to calculate using factorization as the state in which value H at this point is 0. So, tolak aja. So, at 5 bar, ya, jadi si 2961 2961. So, berapa ini? Now, 314 minus 2961. So, you get H is around relative to 700. But 50,705 something. For the U, it's either you can use this table or you can use the shape H equal to U plus PV, sama aja. So, yeah. Continue on Friday. Actually, on Friday, I'm not around. So, we record the session Friday. I have attend a conference. So, face-to-face class will start next week. 28 right? Same place. Question? Yes, I cannot get to the class. I supposed to present during that time. Just watch the video, read the video for this. It's actually continue from this, but there will be exercise. Then we need to submit for the headers. Oh, right. No, okay. Yeah. Okay, thank you.